Okay, welcome everybody. This is a Cincinnati State FS exam review session. Week 2, we're going to look at survey computations and computer applications. My name is Jim Becker, so I'll be stepping you through some problems today. Alright, so we're going to take a look at some basic topics, stuff that you'll probably be seeing on the test, I'm sure. Coordinate geometry, traverse closure and adjustment, leveling, area calculations, horizontal curve, vertical curve, slopes and grades will be included in that. And we don't have volumes yet, but that will be coming. Alright, so the first thing when we look at some of the very basic COGO type applications or things that you would deal with in getting into coordinate geometry, two major areas, I should say inverse and direct. So we got inverse and direct routines, and we'll take a look at that. And then we're going to look at intersections of the bearing type, the distance, and the bearing distance, and we'll be looking at area. Okay, so you guys all understand coordinate geometry, the power of it. We understand how it works for us. Most of it's adapted to digital devices, as we see, because most of us are very used to doing computers and data collectors and those kind of things. But on this test, yeah, you're not going to have all that availability. So we're going to go through some of those simple aspects of coordinate geometry. All right, so first thing is very simply, you guys are probably aware of this, but you're dealing with a lot with either Cartesian or polar data. Being able to convert one to the other. So if you're going from Cartesian to polar, then the radius on your polar value is given by your x and y's. And vice versa, if you're going polar to Cartesian, you can see those equations. All right, so inversing is probably something that you're going to see a little bit more in terms of the kind of stuff you're going to be getting in this test. So inversing is the process where you have a pair of coordinates at two endpoints of a line, northing and easting, or it could be expressed in x and y. And so you can get, from the inverse, you can get direction and or distance, depending on what you're looking for. So if you're looking at pure analytic geometry, we're looking at a delta x, delta y kind of concept, where delta usually refers to final minus initial. So if we're going from 1 to 2, then you notice it's 2 minus 1. And whether they would hit you with x's and y's on this test, I'm not sure, but be prepared, because they could do both x's and y's or northings and eastings. So if we're looking from the surveying standpoint, then it's better to think in terms of latitude departure. So latitude is defined as your change in northings. Again, delta northing, final minus initial, and the departure is your easting directions. Delta easting, easting 2 minus easting 1. So this would give me the true bearing angle. And if we take this concept for direction, we're taking the arctangent of departure over latitude and make sure that it's always departure over latitude. If you reverse that, you're going to get the angle off of the x, and we're always working off of north or the y value. Okay. So if you are doing an inverse problem, because when you do the inverse with your calculator, your arctangent is only going to give you an angle 0 to 90, so what you're getting is a true bearing angle, not an azimuth ever. So you have to determine your bearing quadrant based on the sign of your latitudes and your departures. So we always think that north is positive and south is negative for latitudes, and east is positive and west is negative for departures. So you can either memorize this chart or just memorize the fact that north is positive and east is positive, and then you can kind of determine it any other way based on that. Alright, so distance is a lot more straightforward. We don't have to worry about the signs on that, because they're going to come out when you square them. But basically you're just taking your delta x squared plus your delta y squared square root, and in surveying it's a latitude squared departure squared square root. So a lot less mistakes are going to occur due to distance. In fact, no mistakes should occur due to distance, but angles are the things that we have to really pay attention to. Alright, so here's a quick example. We have a given set of coordinates here, 0.101, 102. You can see the values we got. Those are in terms of northings and eastings, so we're going to step through this problem real quick. Okay, so we're looking at that problem that was on the slide. We're looking at an inverse routine. assuming you're given something like this, you notice we've got point 101 with its coordinate values and point 102 with its coordinate. I mean, they may tell you where north is, they may not, but you should be able to look at your coordinates and understand that north is straight up on this diagram. So if we inverse, we want the distance and direction from either 102 or 101. So let's assume we're going 101 to 102. So the first thing we want to do is grab the latitudes and the departures. So latitudes, if you're going 101 to 102, it's going to be the northing of 102 minus 101. So notice what that does, and that also establishes a sign. If you flip them, you'll get the absolute value, but you'll get the wrong sign, which will kill you when you get into your angle component. Departure works the same way. You notice departure, we have the departure values there. We're going 101 to 102, so we are 102 minus 101 in that case, and notice we get a negative. So that's indicating a northwest direction by looking at those. Okay, so to get the direction, then we would use the arctangent relationship. And we notice now that we have the bearing. Notice it's always going to be a bearing. Remember, you're never going to get an azimuth out of this. So we're going to take the departure over the latitude. I really don't worry about the sign because all that does is gives you a negative angle, okay? But I apply the signs based on what's happening at the end. So when I take the arctangent of the departure over the latitude, you're going to get 78, 41, 26. And looking at my latitude, which is north, that's positive, and west is negative, so we have a northwest bearing, so that would be the direction. Straightforward for distance. Distance is just the Pythagorean theorem. Taking the latitude squared plus the departure squared. Again, don't worry about negative signs because they're gonna come out anyway. And so we're looking at a distance of 660.67 and a direction of 78, 41, 26 northwest. Okay, so direct routine in surveying is kind of the reverse of what inverse is. So in this case, you're given a starting coordinate and you have a bearing and a distance from that coordinate, and you want to come up with a coordinate value at the end point of the line. So what you would do is calculate a latitude and a departure from your starting point to your ending point based on that distance and that bearing that's given. So latitude is distance times cosine of theta, and departure is distance times sine of theta. Now theta can be expressed as either bearing or azimuth. The advantage to azimuth is that if you use an azimuth, you're going to get a sign correctly from your calculator. So you'll get the negative or the positive sign. If you use the bearing angle, it will be up to you to determine whether you're positive or negative on your latitude and departure. Because a bearing angle is between 0 and 90, cosine and sine between 0 and 90 are always going to be positive. So once you have your latitude and the departure, you just apply them to your ending or your starting coordinate. So in this case, if my ending coordinate is B, I'm coming from my starting coordinate northing plus the latitude algebraically. That's giving me that coordinate, and then the ending coordinate E, the easting of B, is going to be the starting of that line plus the departure again algebraically. Okay. So we're going to look at this little simple example again, using that same thing we just had before reference. We're starting at point 101 with the coordinate values that are given there. And we are asked to calculate the coordinate at 50, the end point of the line, at a 400-foot distance and a southwest bearing of 8657.25. Okay, so we're looking at this problem. Again, we're starting at 101 with given coordinates. We're looking for 50. We have the bearing and distance information. So we're going to break that down into latitude and departure. So the first thing is latitude. Remember, latitude is your distance times the cosine of your bearing angle. And in this case, I get the negative sign because I know it's south, okay? If you converted that to an azimuth, you would have gotten the negative sign. Departure is equally getting very easily, it's a sine relationship. Distance times sine of my bearing angle. Again, it's west, so I know that it's negative, but if I put that in terms of azimuth, I get the negative. So then we're going to add these algebraically to the starting coordinates. So notice 50, we're starting from 101's northing, we're adding it algebraically, and we get the 5104. We go to the next point, and we get the 4,600. And that's a direct routine, very simple. So the next aspect we're going to take a look at in terms of coordinate geometry are intersections. Intersections are very powerful ways of establishing points that weren't occupied. So you have three classic intersections: the bearing-bearing type intersection, sometimes called direction-direction, and then you also have the bearing distance type of intersection, which could also be called a direction arc intersection, and then you have the classic distance-distance or arc-arc intersection. So we're going to consider the bearing-bearing first. Bearing-bearing is a case where you have known coordinates at the endpoints of a line, and you have bearings from each endpoint that are basically shooting towards each other. So this will yield an intersection as long as those bearings aren't parallel. If the bearings are parallel, you have no intersection, which should be obvious. So what happens is when you do this, those two bearings, when you're basically shooting them towards each other, they're going to solve an intersection based on a triangle. And this then allows you to determine the unknown positions of those coordinates. So this is a classic example of a bearing-bearing type intersection. Notice we have two coordinates known, A and B, and we have a known bearing from A, and we're just kind of shooting that out any direction. So distance, remember, is not an issue at this point. And B, we have the other bearing that's shooting out, and we're going to get a solution at point C. So that's what we're looking at. So we're going to step through the math on this real quick. All right, so this is an example of a bearing-bearing intersection problem, the one we were just looking at. Notice we have A and B given, northings and eastings at both points. So the first thing we want to do is determine the direction and distance A to B. Okay, so we're going to do that through latitude and departure. Notice at the top I've calculated latitude and departure. I inversed A to B, which gives me the positive directions. If you go B to A, make sure you pay attention to that. By taking the bearing, departure over latitude, I came up with a northeast. If you were going B to A, that would be southwest, of course. So the distance is going to be important for this process because we need a distance because we're going to ultimately solve a sine law relationship here. So I got a distance of 336. I also usually float that out maybe one decimal place more than what I'm given in my coordinates. That preserves a little bit more of the precision when you get into the sines. All right, so having now bearings on all three sides, I can get angles at A, angles at B, and angles at C. So now we can solve a distance, and what we're looking for is a distance either A to C or B to C, because we're going to use that to do a direct routine to solve point C. So I chose to go AC, and notice I set up the sine law. AC is to the sine of B, as AB is to the sine of C. By solving that relationship, I come up with my 268.53 distance. That would be the distance from here to here. Okay? Now the reason I'm doing that is I'm going to solve an angle here. Well, I already know this angle actually. By taking that angle, I can solve the bearing. Okay, or actually an angle, excuse me. So I can get that up. So let's go there. Okay, so knowing the angle of the bearing along AC, when I have the bearing along AC and I have the distance along AC, I can now calculate a direct latitude and departure using a direct routine. So the distance AC times the cosine of that direction gives me a latitude A to C, and the departure is the distance times the sine of that angle. That gives me my departure. And again, the sines of those values are coming from the sine of my bearing. So you have to pay attention. I'm north here and east here. That's why they're plus. Okay. Now we're going to add those directly to the coordinates of A. Okay. So notice the northing of A plus the latitude A to C, that gets me my ending coordinate of 1426, and then we have the easting of A plus the departure A to C will give me that 1751 of EC. So the next intersection we're going to take a look at is the bearing distance type intersection. A little bit harder to deal with, but it's the case where you have known coordinates at endpoints of a line, known bearing from one of those endpoints, and a known distance from the other, which you can think that known distance is actually a radius, so it generates an arc around. But where the intersection occurs, you get a triangle that forms, and you can solve the intersection via triangle solutions. But this will typically yield two solutions. There's only one unique case where it would yield one, and if the radius of the arc is too small, it would yields 0. So when you have the two-solution problem, you have to know which one you're talking about. Okay? But this does allow you to determine the unknown coordinates. So if we look at this picture, you'll notice we have coordinates A and B given. Well, that's the line that's fixed. And then we have a bearing from A of north 733610 east. Now what you're clearly seeing hopefully in that B point, that's where my arc is actually occurring. And you notice if I swing the arc to the left with its radius value, it intersects at C. But there's also another point out there which we might call C prime. So in this type of problem, you would have to be told which solution you're looking for, because if you did this, say, on a computer, you may not know which solution. So we are looking for the angle there at C, okay? Or we're going to look at the solution at C. So here's the problem drawn out, and from a stepwise process, you've got A and B. The first thing you want to do is get a latitude and departure, A to B or B to A, depending on which direction you're going. I chose to go A to B, so notice my latitude is south, it's a negative, and my departure is east. So from that, I'm going to get a bearing, I'm going to get a distance on the line AC. So again, bearing is departure over latitude. I get 692234, and south is coming from the latitude, and close is coming from that departure east. Distance 732, excuse me, 0.301. Again, I like to carry that out a little bit more. So now then we can look at solving an angle. What we need to do is solve, we got an angle at A very clearly because we have two bearings, but we need to get at least another angle because we have some distances and we have some angles, but we need other angles. So what we're going to do is do a sine law, and we're going to solve the angle at C because we have an angle and a distance. So notice we have an angle opposite a distance, and we're going to come up with another distance here, okay, or another angle rather. So what I'm doing is a sine law, saying the sine of C is to its distance its opposite, which is the one we just calculated, as the sine of A is to the side its opposite. What that does is yields me an angle of C, 712618. But that's a very small angle, and if you notice, because of the way the sine law works, this is sometimes called the ambiguous case. So we're getting the smaller angle here as opposed to this larger angle here. So what we have to do is subtract that angle from 180. So that's, again, that's the decision you have to make. So the actual angle at C that I'm looking for is the 180 minus the C. Okay, so notice we then come up with that 342502. All right, so the next thing now is knowing that we have that, we can solve that as a bearing. Okay, so we get the bearing from B to C, and knowing the bearing B to C, we can then take and solve the latitude and departure. So do understand here, this angle is not the same thing as this angle. If you'll notice, this is the internal angle, but this is the bearing that is solved from that side and that angle that you just had. Okay. So what you have there then is that northwest bearing. Knowing that northwest bearing, you have your distances, take your cosine, direct routine gives you the latitude and then the departure, and then those get applied to your northings of where you're coming from, in this case B plus the latitude BC, and E plus the departure BC. Okay? So this one's a little bit more involved because you have to deal with what solution you're dealing with and whether you're getting that ambiguous case of the sun. So the last type of intersection we're going to look at is what's called a distance-distance intersection, also commonly referred to as arc because you're swinging two arcs. So you have known coordinates at the endpoints of a line, and you have a distance from each endpoint, and again those would reference or be your radius points essentially. So where these two intersect will give you, your two arcs are going to intersect and give you your solution point. So we can solve this by triangles. And the thing is that this may also yield two solutions. In fact, it typically will yield two solutions. The thing about it is it could also yield one solution, and that's very rare, and then it could yield none if the arcs don't intersect, obviously. So you also then have to determine which intersection you're talking about, but this one's a little bit easier than looking at the last one. But this will then allow us, where that intersection occurs, to determine the unknown coordinates. So this is a picture of a kind of example. Now what you see here is A and B that are given points with coordinate values, and you have two distances given. The distance from B would be the radius of that arc, and it's 232.44, and the other one is 176.20. So you can see I've kind of clipped the two arcs, but if you extend those arcs down, they would actually be down below here. So they would be occurring down here on the opposite side. So they're really just going to be opposite each other. So it's pretty clear on this one what you're dealing with when you're dealing with this type of intersection. So here's our distance problem. You notice we have the points A and B that are given with their coordinate values, and we have the distances from A to C and B to C. I'm not drawing the arcs in here for clarity, but that's what you kind of got to visualize what's going on. So again, like the other two problems, the first step is to inverse, so we get a bearing and a distance. So notice my latitudes and departures at the top. I'm inversing A to B, and again, they came out both positive, so that's a northeast direction. So my bearing there is 83.717 northeast. My distance turned out to be 329.643. So we're going to be able to utilize that now, utilizing the cosine law. So what we're looking for in this case, we have one angle, which we can, well, we actually have no angles. So we just have one direction. But what we do have is distance, 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 so that allows me to solve one of the other types of angles. So what you want to do is you want to solve an angle that's smart for you. This angle is probably not going to be valuable, but the angle here or here is going to be real useful. So what I'm doing is choosing to solve the cosine of A. That'll give me this angle, because once I know this angle, I can solve this bearing. So notice I'm using the cosine law, plugging in the values of distance, which I know, but I don't know the A, so I back that in and solve the cosine of that, and ultimately taking the arc cosine of this relationship gets me that 42.2826. So knowing that value, I can then get this bearing, because I know that bearing, and so I can solve that. So what I've done is then solve the bearing AC by basically taking and subtracting that from my my 83.717. So that's where I came in with that. Then from that point, it's a direct routine. So what we're going to do is again taking the
What do you want to show? Just let it do the part.
Oh, you're good. You're good. Just you can go off. That's fine. Ready? So we're taking and calculating latitude and departure of that line AC, because we know its bearing and we know its distance. So again, we get our latitudes and departures, and we apply those to the coordinates directly. So again, latitude plus the northing of the point you're coming from, departure plus the easting of the point you're coming from. And that's your solution for that type of intersection. Okay, so the last coordinate thing we're going to look at under coordinate geometry is area calculations. I'm going to just show you the process real quick, but we're going to do an example here when we get into area. So basically, you have, let's say, given coordinates on a traverse or a boundary or whatever. In this case, I've got a three-sided traverse or boundary A, B, and C. So what we have is you either in terms of northings and eastings or x's and y's, and it really doesn't matter, but you just write your x's in one side and your eastings or northings on the other, or whatever. And what you've got to recognize when you do this problem, if you start with A, you have to end with A. So if you have three sides, you're actually going to have four values here. Okay? If you forget to do that, you're not going to have a closed figure. You'll get a value, but it will be completely wrong. So all you do to do this, you can multiply across red to red this way or this way. It doesn't matter which way you start. I usually just go this way. Okay, so I'm going to stake x of A times Y and B. Notice I write it down here, but we're going to consider that a positive product, okay? Then we're going to go B to C, and then we're going to go C to A. So you're going to have 1, 2, 3 positive products, because in this case we have 3 sides, okay? If you have 4 sides, you'll have 4 of those. 5 sides, 5. So you always count that. Then when you're going to go the other direction, we're going to do it negatively. So we're going to do this times this, and we're going to call that product negative. B times C, we're going to call that product negative. And C times A, we're going to call that product negative. When we take those products and we add them algebraically, it will yield us 2 times the area, to which we divide it by 2. You can get a negative sum, okay? And a negative sum only indicates you run around it counterclockwise, I believe. So it doesn't mean anything, okay? No, it's not a mistake.